Let's look at simple harmonic motion. The best model for simple harmonic motion is a spring, and in particular we're going to be using the ideal spring, where we assume that the coils of the spring will compress or stretch by the same amount, not some stretching more and some less. That's what we mean by this ideal spring. So here we have a little example of a spring that's connected to this car, and the car is going to be moving back and forth, and we want to see how the spring stretches. So we look at the length of the spring basically. So here we go. The spring is stretching and compressing, undergoing simple harmonic motion. So I'm going to do this again, and I'll try to pinpoint the extremes, the minimum length and the maximum length of the spring. So let's see how we can do this. All right, so I kind of exaggerated here a little bit. But these 2 points are the turning points where the car is going to go to the left at this point, the car is going to go to the right at this point. In between these 2 points, halfway in between, is what we call the rest length or the equilibrium length of the spring. So this would be a compression X, and this would be a stretch X. And the object, the car, oscillates between these two extremes. So if it starts from rest, we stretch it, and as we're stretching it, the spring is going to pull back on it, and then it's going to pass through equilibrium, it's going to get to the maximum compression, and the spring is going to try to push it back to equilibrium. So the spring oscillates back and forth between these two extremes. So here we have a drawing of this. So in the middle we have equilibrium. So this is the equilibrium position of the spring. And in this situation, in the first situation, we have an applied force. I'll call it F applied. And the spring will want to oppose that with some sort of spring force. So I'm going to call it spring elastic force. So I have F elastic here. Now in the third situation, I am actually stretching the spring. So the applied force is to the right, and the spring's response is to pull back on it. So this will be the elastic force, the spring force, trying to bring the spring back to equilibrium. So this elastic force is going to be a restoring force. It wants to oppose anything we do to the spring so that it will bring the spring to its equilibrium position. It wants to restore the original equilibrium position of the spring. So here we apply the force to the left, the spring will act to the right. Here we apply the force to the right, the spring will want to go to the left and restore the equilibrium position. So we say that the spring force is proportional to the stretch or compression from equilibrium, and that proportionality constant is called the spring constant. So K here is the spring constant of the spring. It's a function of the material that the spring is made out of, a function of the thickness of the coils, various things like that. Now the negative sign stands for the fact that the spring force is a restoring force. So whatever we're trying to do to it, the spring force will act in the opposite direction. This equation is called Hooke's law. So the equation for the spring force, for the elastic force, is given by Hooke's law. Now, it's easy to see, to compare this simple harmonic motion to something that we've known from before, the reference circle. So here I have a demo. We have this dot circling around counterclockwise in this situation. And this is something that we've noticed, that we've seen in trigonometry when we learned sines and cosines. So let's look at it again. And now notice that this dot is actually a projection onto the x-axis of the dot that's going around the circle. And this dot here just basically goes back and forth just like the spring did in simple harmonic motion. So let's try to draw this on here. So if this would be the radius of my circular path, I'm going to call it A, and I'm going to draw a projection onto the x-axis. I have this triangle here, and that would be side x, and this would be angle theta. So I can say that x is a cosine theta. But remember from rotational motion that theta is omega t. Basically, what I have is that angular velocity is angular displacement divided by time. So what this also means is that this particular dot here is actually going to go between two extremes. So these extremes are what we call the amplitude. That's why I called it A. So that would be the radius of the circle. So the extremes are A and negative A, and the x is going to fluctuate between them in a cosine theta fashion. So it's maximum initially, and then because we have to stretch the spring to set it in motion, we can't just leave it in equilibrium and expect it to oscillate. We have to first stretch it or compress it, and then the spring, the x of the spring, will oscillate back and forth between the two maxima, the amplitudes. So here is a drawing of a cosine wave. It's much easier to see the cosine wave than the image that we had before in the video. And we said that x is a cosine omega t. So a is the amplitude of the motion, and the x goes as cosine omega t again, because first we have to stretch the spring from equilibrium to get it moving. Now, if we take the derivative of x with respect to time, we end up with negative omega a sine omega t, and that gives us the velocity of this motion. Taking the derivative one more time, we end up with negative omega squared a cosine omega t. So one thing to note here is the fact that this quantity, a cosine omega t, was actually the x. So we can say that a is negative omega squared x. All right. So one more thing to note here is that since a sine wave or a cosine wave goes between 1 and negative 1, then when we want to set v or a maximum, we will actually just set the sine or the cosine to their maximum. So we have the maximum values. V max is negative omega a times sine omega t, which we set as maximum, and that's 1. So the V max then is negative omega a plus or minus omega a, and A max is going to be negative omega squared times a, where we set the cosine equal to plus or minus 1. So we want it to be maximum. The function has to be maximum, and that gives us 1 for cosine or sine. All right, so we looked at displacement, velocity, and acceleration, but let's just look at the sine wave and remember a few things about, about the cosine wave. Remember a few things about the shape of the wave. So I mentioned already the amplitude of the wave, where the amplitude is the maximum displacement from equilibrium. Another very important quantity is the period. So the period is the amount of time it takes for the motion to repeat itself. So period would be from this point to that point, because this is where the wave starts going back up. It could also be from here to there, from here to here, from somewhere there to somewhere there, anywhere where the motion repeats itself. And it's usually easier to just find it at either the valleys or the peaks. But any time the motion repeats itself, that's where one period ends. Then 1 over the period is the frequency, and frequency is measured in inverse seconds, and there's a special unit for that called hertz, and the symbol is just Hz. Then angular frequency is 2 pi over the period, or 2 pi times this frequency. So this is called angular frequency, and it's measured in radians per second. Remember that we saw this in circular motion. We called omega just angular velocity. And there is a relationship between angular velocity and angular frequency. They're basically the same thing. It's just that you'll have to think about it in a little bit different way depending on which situation you're in, what types of problems you're dealing with. So how about we now derive the frequency of vibration? So by Newton's second law, we know that the sum of the forces acting on an object that's oscillating back and forth just like the car is equal to mass times acceleration. Well, the force that acted on the car was the spring force, so that was negative kx, and that's equal to mass times the acceleration that's given in here, negative omega squared a cosine omega t. Well, we know that x has this form, so we're going to substitute that and end up with negative k times a cosine omega t is equal to negative m omega squared a cosine omega t. So I can cancel out cosine omega t, I can cancel out the amplitude, and end up with omega being square root of k over m. So we'll say that the frequency of vibration is this omega, which is square root of k over m. So here is the equation again, and then if we use these two, these two relationships between angular velocity or angular frequency, period, and frequency, we end up with the period of vibration being 2 pi squared of m over k, and the frequency being 1 over 2 pi squared of k over m. Now, one very important thing about this spring force is that it's only a function of the displacement, and that means that it's a conservative force. Every conservative force has a potential energy associated with it. And it also makes sense because if you think about a spring, you're compressing it and you're storing energy in it. You know that it's going to decompress, it's going to try to go to equilibrium and dissipate that energy into a different form of energy. So the spring has stored energy, a potential energy, and that potential energy stored in the spring is a function of the spring constant and the displacement from equilibrium. So spring potential energy is 1/2 kx squared. Now we know that if we set the little car demo that I had, if I set that in motion, after a while it will stop. That's what we call damped harmonic motion. So what is happening is the amplitude keeps decreasing. So the amplitude goes down, but the period and frequency stay the same. So it's only the amplitude that is damped, that is decreasing in time. So that is not always convenient. If we have a grandfather clock, a cuckoo clock, the ones with the pendulum on the bottom, if they behave like this, then they won't keep time very well. So we have to drive that harmonic motion, and we drive it by setting the driving frequency equal to the natural frequency of the oscillator. So this natural frequency is the frequency that the particular oscillator has based on its shape and some other different characteristics that it has. We'll look into that. We'll look into pendulums in a future lecture.